Welcome to this coding walkthrough, where we'll tackle LeetCode problem number 148, sort list. In this problem, we'll explore how to sort a linked list efficiently in ascending order. We'll analyze the key challenges of working with linked lists and discuss an optimal solution. Let's dive in. In this problem, you are given the head of a linked list, and your task is to sort the list in ascending order and return the sorted version of the list. Let's take a look at the first example. The input linked list is 4, followed by 2, then 1, and finally 3. When this list is sorted, the output becomes 1, followed by 2, then 3, and finally 4. The goal is to transform the input list into this ordered structure while maintaining the constraints of the problem. Now, in the second example, the input linked list contains the values -1, 5, 3, 4, and 0. After sorting, the output list becomes -1, followed by 0, then 3, 4, and finally 5. This demonstrates that the solution must handle both negative and positive values efficiently. In the third example, the input is simply an empty list. Since there's nothing to sort, the output is also an empty list. This edge case highlights that the solution must correctly handle scenarios where the list has no elements. To summarize, there are a few important constraints to keep in mind. First, the number of nodes in the list can range from 0 to 50,000. Additionally, the values of the nodes can range from -100,000 to 100,000. The solution must be efficient, running in n log n time complexity. It's also important to note that you are not allowed to directly modify the values of the nodes to sort the list. Instead, you'll need to rearrange the nodes themselves while adhering to these constraints. To solve LeetCode problem number 148, which requires sorting a linked list, we first need to consider approaches that align with the unique properties of linked lists. One straightforward method is the brute force approach, where we convert the linked list into an array, sort the array using a built-in sorting algorithm, and then reconstruct the sorted linked list. This method involves 3 key steps: traversing the list to store node values in an array, sorting the array, and rebuilding the list with the sorted values. While this achieves the sorting in n log n time and is conceptually simple, it introduces significant drawbacks. The extra memory required to store the array violates the problem's constraint of 1 extra space, and it doesn't leverage the inherent structure of linked lists. This makes the brute force approach suboptimal for this problem, prompting us to explore more efficient strategies. A more optimal solution is to use merge sort, which is well suited for linked lists. The intuition here is that merge sort operates on a divide and conquer principle, and linked lists allow efficient splitting and merging. First, we split the list into 2 halves using the slow and fast pointer technique. Each half is then recursively sorted, and the 2 sorted halves are merged together into a single sorted list. This approach achieves n log n time complexity due to the recursive splitting and merging steps, and it meets the space constraint with only log n space required for the recursion stack. Merge sort not only avoids the memory overhead of creating an auxiliary array but also effectively utilizes the linked list structure, making it a natural choice for this problem. Its efficiency and compatibility with the problem's constraints make it a strong candidate. Another alternative is the bottom-up merge sort, which is a non-recursive version of merge sort. Instead of recursively splitting the list, this method uses an iterative approach. It starts by treating individual nodes as sublists of size 1, and then repeatedly merges these small sublists into larger sorted sublists until the entire linked list is sorted. This approach maintains the same n log n time complexity as recursive merge sort but eliminates the recursion stack, achieving 1 space usage. However, the trade-off is that the bottom-up approach is more complex to implement, as it requires additional logic to handle iterative merging in sublist management. While it is efficient in both time and space, its implementation complexity makes it less attractive compared to the recursive merge sort. Based on these considerations, recursive merge sort remains the preferred solution. The key insight for solving this problem is understanding how naturally suited merge sort is for linked lists. Unlike quicksort or other algorithms, merge sort efficiently handles linked lists due to the ease of splitting and merging. Additionally, the recursive merge sort satisfies the 1 extra space constraint, apart from the recursion stack, making it an ideal choice for this problem. When comparing the approaches, the brute force method is simple but fails to meet the space constraint, while the bottom-up merge sort eliminates recursion but adds unnecessary complexity. Recursive merge sort strikes the right balance, offering optimal performance and simplicity while leveraging the linked list structure. Overall, it stands out as the most efficient and practical solution for sorting a linked list in ascending order. To solve the problem of sorting a linked list efficiently, we use the merge sort algorithm, which is particularly well suited for this data structure. The first step is to handle the base case for recursion. If the input linked list is empty or consists of just one node, it is already sorted. This is because a single node or an empty list doesn't require any further sorting, and we can simply return the head node. Next, we split the linked list into two halves. This is achieved using the fast and slow pointer technique. By initializing both pointers at the head of the list, we move the slow pointer one step at a time while the fast pointer moves two steps. When the fast pointer reaches the end of the list, the slow pointer will be at the middle. This allows us to divide the list into two parts by breaking the link at the middle. For example, a list like 1 2 3 4 is split into 1 2 and 3 4. This division is crucial for the recursive merge sort process. Once the linked list is split into two halves, we proceed to sort each half recursively. The left half is passed into a recursive call to the sortList function, and similarly, the right half is handled in a separate recursive call. This ensures that each portion of the list is broken down and sorted independently. After sorting the two halves, we merge them back together. The merging process combines the two sorted linked lists into a single sorted list. To do this, we use a dummy node, which simplifies the task of managing pointers during the merge. A pointer, often called current, is used to build the merged list starting from the dummy node. We then compare the values at the heads of the two lists, adding the smaller value to the merged list and advancing the pointer on that list. This process continues until one of the lists is exhausted, at which point the remaining nodes from the non-exhausted list are appended to the merged list. Finally, we return the merged list starting from the node after the dummy, which gives us a sorted combination of the two halves. Merge sort is particularly effective for linked lists, and there are important reasons behind this choice. Unlike algorithms such as quicksort or heap sort, merge sort does not require random access to elements, which aligns well with the sequential nature of linked lists. The operations of splitting the list and merging the halves can be performed efficiently using pointer manipulation. In terms of efficiency, merge sort runs with a time complexity of O(n) log n. This is because the list is repeatedly divided into halves, which happens log n times, and each merge operation processes all n nodes. The space complexity is O log n, stemming from the recursive calls stored on the stack. The fast and slow pointer technique is a key aspect of the algorithm, allowing us to find the middle of the list in O(n) time without consuming extra memory. These characteristics make merge sort an optimal choice for sorting linked lists. The algorithm relies on a few essential data structures and techniques tailored to the nature of linked lists. First, the input itself is a singly linked list, and all operations, such as splitting and merging, are performed directly on the nodes. During the merge step, we use a dummy node to simplify pointer management. The dummy node acts as a temporary starting point for the merged list, making the process of appending nodes more straightforward and avoiding the need for special handling at the beginning of the list. Additionally, there are several edge cases to consider. If the input is null, meaning the list is empty, we immediately return null since there is nothing to sort. Similarly, if the list contains only a single node, we return that node as it is already sorted. For lists with duplicate values, the algorithm naturally handles them because it compares values directly during the merge step, ensuring that duplicates are preserved in the correct order. Another scenario that this algorithm handles seamlessly involves negative values. Since comparisons between numbers are performed using the less than operator, the algorithm works correctly with negative values just as it does with positive values. This ensures that the sorting process is robust and can handle a wide range of numerical inputs without requiring any special adjustments. With all these considerations, the merge sort algorithm provides a comprehensive solution for sorting linked lists efficiently and effectively. Here, we start by defining the listNode class to represent the nodes of our linked list. Each node contains a value, val, and a pointer to the next node, next. Then, in the solution class, we define the sortList function, which will implement the sorting logic. The first step in this function is to handle the base case. If the list is empty or contains only one node, it is already sorted, so we simply return the head. Next, we proceed to split the list into two halves. Using two pointers, slow and fast, we traverse the list at different speeds. The slow pointer moves one step at a time, while the fast pointer moves two steps. When fast reaches the end, slow will be at the midpoint of the list. We then split the list by severing the connection at the midpoint. The first half remains with the head, while the second half starts from mid, which is slow. Next. After splitting, we recursively call sortList on both halves to sort them individually. Finally, we merge the two sorted halves by calling a helper function, mergeToLists, which we will define shortly. The mergeToLists function handles the merging of two sorted linked lists. To begin, we create a dummy node to simplify the merging process. This dummy node acts as a placeholder, and we use a current pointer to build the merged list. While both input lists, L1 and L2, have remaining nodes, we compare the values at their current positions. If the value in L1 is smaller, we link the current node to L1, and move L1 to its next node. Otherwise, we link the current node to L2, and move L2 forward. In either case, we advance the current pointer to the newly linked node. Once one of the lists becomes empty, we append the remaining nodes of the other list to the merged list, as they are already sorted. Finally, we return dummy.next, which points to the head of the merged list. This completes the merging process and ensures that the sortList function can return a fully sorted linked list. Here, we start with the definition of the listNode class, which represents a node in our singly linked list. Each node contains an integer value and a reference to the next node. We also provide multiple constructors for flexibility when creating nodes. Next, we define the sortList method, which takes the head of the linked list as input and returns the head of the sorted list. The first thing we check is the base case. If the list is empty or contains only one node, it's already sorted, so we simply return the head. If the list has more than one node, we proceed to split it into two halves. To do this, we use the slow and fast pointer technique. The slow pointer moves one step at a time, while the fast pointer moves two steps, allowing us to find the midpoint of the list efficiently. This setup helps us prepare for breaking the list into two smaller sublists. Now, we continue to locate the middle of the list. The while loop ensures that the fast pointer moves twice as fast as the slow pointer, and when the fast pointer reaches the end, the slow pointer will be at the midpoint. Once we find the midpoint, we break the list into two halves by setting the next pointer of the slow node to null. This creates two separate linked lists. After splitting, we recursively call the sortList method on each half. This divides the problem into smaller subproblems, following the divide and conquer strategy. Once the two halves are sorted, we merge them back together. To perform the merging, we use a helper method called mergeToLists, which combines two sorted linked lists into one sorted list. In the mergeToLists method, we use a dummy node as a placeholder to simplify the merging process. A current pointer starts at the dummy node and helps us build the merged list. While both input lists have remaining nodes, we compare their values. If the value in the first list is smaller, we attach the node to the merged list and move the pointer in the first list. Otherwise, we attach the node from the second list and move its pointer. The current pointer is then advanced to the newly added node. After the loop, we check if there are any remaining nodes in either list. If so, we append them directly to the merged list since they are already sorted. Finally, we return the merged list starting from the node after the dummy node. This completes the merge operation and ensures the resulting list is fully sorted. To begin solving the problem, we start with the input linked list 4, 2, 1, 3. Our first step is to split the list into smaller parts using the slow and fast pointer technique. Initially, the slow pointer is at the first node, 4, and the fast pointer is at the second node, 2. As we move the slow pointer one step at a time and the fast pointer two steps, the slow pointer reaches 2 while the fast pointer lands at 3. At this point, the fast pointer reaches the end of the list, indicating that the middle of the list is at node 2. We then split the list into two halves, the left half, 4-2, and the right half, 1-3. Next, we recursively sort each half. For the left half, 4-2, the slow and fast pointers identify the middle as 4, splitting it into two single-node lists, 4 and 2, which are already sorted. Similarly, for the right half, 1-3, the middle is identified as 1, splitting it into 1 and 3, which are also single node and therefore sorted. Now that we have sorted halves, we move on to merging them. Starting with the left half, we merge 4 and 2. Comparing the two, 2 is smaller, so it is added to the result first, followed by the remaining 4. This gives us the sorted left half, 2-4. Similarly, for the right half, we merge 1 and 3. Comparing these, 1 is smaller and added first, followed by the remaining 3, resulting in 1-3. Finally, we merge the two sorted halves, 2-4 and 1-3. Comparing the heads, 1 is smaller, so it is added first. Next, we compare 2 and 3, and 2 is added. Then, 3 is compared with 4, and 3 is added. Lastly, the remaining 4 is added to the result. The final merged and sorted list is 1-2-3-4. In our second example, we start with the input linked list, -1, 5, 3, 4, 0. Using the slow and fast pointer technique, the slow pointer starts at -1, and the fast pointer at 5. As we move the pointers, the slow pointer advances to 5 and then to 3, while the fast pointer moves to 4 and then reaches the end of the list. This identifies the middle as 3, splitting the list into two halves, -1-5-3 and 4-0. For the left half, -1-5-3, we split it further into -1-5 and 3. The leftmost part, -1-5, is split into single node lists -1 and 5, which are then merged. Comparing -1 and 5, -1 is added first, followed by 5, resulting in -1-5. Now, we merge -1-5 with 3. Comparing -1 and 3, -1 is added first, then 3, and finally 5, giving us -1-3-5. For the right half, 4-0, we split it into 4 and 0, and merging these gives 0-4. With the two have sorted, we now merge -1-3-5 and 0-4. Comparing the heads, -1 is smaller, so it is added first. Next, 0 is smaller than 3, so 0 is added. We then compare 3 and 4, and 3 is added. Comparing 5 and 4, 4 is added next. Finally, the remaining 5 is added to complete the merge. The final sorted list is -1-0-3-4-5. In our third example, the input linked list consists of just one node, 1. Since it is a single node list, it is already sorted, and we simply return the node as is. To summarize, the algorithm employs a divide and conquer strategy, breaking the list into smaller parts recursively and then merging them back together in sorted order. The merging process utilizes a dummy node to simplify edge cases, ensuring a smooth and efficient merge. The time complexity of the algorithm is O, n log n, where n is the number of nodes, due to the repeated splitting and merging steps. The space complexity is O log n, as the recursive calls contribute to the stack depth. These examples demonstrate how the algorithm handles various scenarios, including small lists, lists with negative numbers, and lists that are already sorted. The time complexity of the sort list function is O, n log n, where n is the number of nodes in the linked list. This complexity arises from two key operations, splitting the list and merging the sorted sublists. First, when splitting the list, we use the slow and fast pointer technique to divide the list into two halves. This requires a single traversal through the list, which takes O, n, time for a list of size n. Since the list is repeatedly divided in half at each recursive level, the total number of levels is proportional to log n, starting from the original list size n and halving until we reach lists of size 1. This gives us the foundational log n depth for recursion in the algorithm. Once the list has been fully divided, the merging process begins. Merging two sorted lists of total size n involves comparing and linking the nodes in order, which requires O, n, time for a single merge. Across all recursive levels, each node in the original list is processed exactly once during the merging phase. For example, at the top level, two halves of size n/2 are merged, at the next level, 4 chunks of size n/4 are merged, and so on. This ensures that merging at each level takes O, n, time. With log n levels of recursion, the total time for merging across all levels becomes O, n log n. For space complexity, the recursive implementation requires stack space for each level of recursion. Since the depth of recursion is proportional to log n, the space complexity for the function call stack is O log n. In addition to the recursive stack space, the merge2lists function uses only constant space. It employs a dummy node and a pointer for traversing and rearranging the input nodes, but it doesn't allocate additional memory for new nodes. This in-place merging ensures that the algorithm doesn't require any extra auxiliary data structures. As a result, the overall space complexity of the sortList function is dominated by the recursion stack, which is O log n. Now, analyzing the best, average, and worst cases, the time complexity remains O n log n for all scenarios. Even if the list is already sorted, merge_sort still divides and merges the list. Similarly, for a reverse-sorted list or a randomly ordered list, the divide and conquer operations proceed in the same manner, maintaining the O n log n efficiency. When comparing with other approaches, simpler methods like extracting the list values into an array, sorting the array, and reconstructing the linked list require O n space for the array and O n log n time for sorting. However, this method isn't in place. Another naive approach involves repeatedly finding the minimum or maximum node and rearranging the list. This has a time complexity of O n squared, as finding the minimum or maximum takes O n and must be repeated for each node. In contrast, merge_sort is optimal for linked lists. It achieves O n log n time and O log n space while sorting the list in place. This makes it far more efficient and well suited for this data structure. The time complexity of merge_sort can also be demonstrated mathematically. At each recursion level, splitting the list requires O n time. Similarly, merging all the sublists at that level also takes O n time. With log n levels of recursion, the total time is the product of these two factors, O n, for each level, multiplied by log n levels, resulting in O n log n. This analysis confirms that merge_sort achieves optimal sorting efficiency for linked lists, combining both its divide and conquer methodology and its in-place node rearrangement. When working with this problem, there are several common mistakes that you'll want to avoid. First, many people assume that array-based sorting algorithms, like quicksort, can be directly applied to linked lists. However, linked lists lack random access, which makes these approaches highly inefficient due to the need for O n traversal for each element. Second, edge cases are often overlooked. Scenarios like an empty list, a single-node list, or a list that's already sorted must be handled carefully to prevent runtime errors or incorrect results. Another issue arises when the chosen algorithm doesn't meet the required time complexity of O n log n. Algorithms like bubble sort or insertion sort, which run in O n squared, are not efficient enough for this problem. Additionally, some solutions modify the input list without preserving its original structure, which can lead to unsorted fragments or the loss of the original head node, making debugging extremely difficult. Lastly, errors in the merge step of merge_sort are a frequent pitfall. Properly merging two sorted sublists requires careful pointer manipulation, and mistakes here can result in null pointer exceptions or infinite loops if pointers aren't updated correctly. Now, let's consider insights that can help you succeed in an interview setting. First, it's important to understand the properties of linked lists. The sequential nature of a linked list makes divide and conquer strategies, like merge_sort, a natural fit. Merge_sort works particularly well because splitting the list into halves and merging requires only O1 extra space. Next, tailor your solutions to the constraints given in the problem. If space optimization is emphasized, focus on achieving O n log n time with O1 space, which might lead you toward an iterative approach. It's also crucial to explain trade-offs. For instance, you should be able to articulate why merge_sort is more suitable for linked lists compared to quicksort. Quicksort relies on partitioning, which is inefficient for linked lists due to their lack of random access. Finally, don't just solve the problem, communicate how you've handled edge cases, such as empty or single-node lists, to demonstrate the robustness of your solution. This builds confidence in your approach and shows that you fought through potential pitfalls. Building on that, it's helpful to explore related problems that deepen your understanding and strengthen the skills required for sorting linked lists. For example, LeetCode 21, which involves merging two sorted lists, is directly connected to the merge step in merge_sort and is a foundational skill for solving this problem. LeetCode 23, which focuses on merging k-sorted lists, takes this concept further by emphasizing divide and conquer strategies for handling multiple lists. LeetCode 141, which detects cycles in a linked list, helps you develop precise pointer manipulation skills. These are often critical for debugging and implementing sorting algorithms effectively. Lastly, LeetCode 206, which requires reversing a linked list, sharpens your understanding of pointer operations, a skill that's valuable for both manipulating and sorting linked lists. Working through these related problems can provide a broader perspective and prepare you for variations you might encounter. Finally, let's look at some alternative approaches to solving the problem and the trade-offs associated with each. Recursive merge sort is a popular choice because it's easy to implement and aligns well with the divide and conquer paradigm. However, it uses O log n space due to the recursion stack, which may not meet strict space constraints. Iterative merge sort, on the other hand, avoids recursion and achieves O space, but it requires careful management of sublist boundaries and merging logic, which can make the implementation more complex. Another approach is to convert the linked list into an array, sort the array, and then reconstruct the list. While this method is simple and often fast, it violates the O space requirement and may not be acceptable in interviews where space efficiency is critical. When deciding between these methods, consider the trade-offs. Recursive merge sort is simpler to write and debug but consumes more memory, while the iterative version is memory efficient but more challenging to implement. Sorting via array conversion may be tempting for its simplicity but isn't suitable for scenarios with strict space constraints. Weighing these options carefully will help you choose the best approach for the given problem requirements. Great job following through. We've learned how merge sort is an ideal choice for sorting linked lists and how to handle recursion effectively. Remember, mastering linked list problems builds a strong foundation for more advanced data structure challenges. Thank you for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!